All right. So we're going to learn about the X-ray tube. This is going to be a little bit of revision. I think you learned about some of this before, and uh, I don't think, well, yeah, let's recap a little bit what we've learned so far. So you've learned about current and voltage, and you learned that current is a movement of electrons, and the unit of current is amperes, and voltage is what makes current flow, right? And the voltage has another name. We call that potential difference or electromotive force. And we select those things when we're changing the technical parameters. We select MAS and we select kVp. So now we're going to look at what's happening, what parts of the tube participate in this X-ray production process. So let me start from the beginning. Presenter's view. And this is really, really short. So here are the objectives. We're going to talk about the general design of the X-ray tube. Just remember, we did earlier, in prior weeks, the X-ray circuit, where we looked at the transformers and the rectifiers and the MA meter and the voltmeter and so on and so forth. Now we're looking at just the X-ray tube, right? The thing you should know about this is most X-ray rooms are designed with a ceiling mount system. Ceiling mount. In years past, it would be ceiling to floor, floor to ceiling, where it's connected to both the floor and the ceiling. Most of them are just ceiling mounted. I think when I looked at your lab, the one in your lab is just ceiling mounted. Is that accurate? Is it just a ceiling? Okay, so most of them are ceiling mounted. Make sure you notice this is a thing that I saw on a registry review question. What is the purpose of the X-ray housing? We're going to look at the parts in a second, but make sure you know some of this important stuff here. The X-ray housing protects against electric shock. Well, how does that work? Well, when the electrons are leaving let me pull up an X-ray tube. When the electrons are being released from the cathode to the anode, some electrons are gonna bounce all about the tube. Well, the housing protects you from electric shock and conducts that electricity away from in a safe way so you won't get electrocuted or the patient won't get electrocuted. All right. The enclosure is usually glass or metal, and that's the bit that encloses the cathode and the anode. What's the charge of the cathode? Anybody? Unmute and just say it. Actually, no, I have time to call on people. Hui Ming, what's the charge of the cathode?
Sorry, also I'm in the library to waiting for harassment. Is not really allowed to
I
talk
see. All
out
right.
loud.
All right. Don't worry about it. Go ahead,
Yeah.
Clueless. What do you got for me?
And it's negative.
Okay, why is it negative? What's being released from the cathode?
Electrons.
Okay, got you. When we say the cathode assembly, what's included in the cathode assembly? I'm just testing to see what you know. Let's stick with you, Clunas.
There's the filament and the focusing cup.
Cool. What's the charge of the focusing cup?
It's I'm gonna take a guess and say negative.
Oh, and that would be a good guess. I don't think you're guessing. That's fantastic. All right, cool. So I think this is going to be a quick one for you. All right, so one side of the tube is negative, one side is positive, and it's usually written right on the outside of the tube. The anode is going to be a rotating anode. All machines, all modern X-ray machines are rotating, not stationary. It's going to be a reason for that. We'll talk about it in just a second, all right? All right, so the bit that you should know from here is that most designs now are ceiling mounted. What does the housing do? That's the outer part of the tube. Well, that's the bit that helps to protect you from not just radiation but electrocution, right? And the enclosure is glass, is usually glass, typically glass, and it's vacuum sealed. Why would it be vacuum sealed? Does anybody know? All right, nobody knows that. Go ahead, Virginia. What you got for me?
Is it to prevent like leakage radiation?
No, not quite. Kennedy, what you got for me?
Is it to prevent the electrons from interacting with the air, like from any other molecule?
That's exactly right. Conlan, was that what you were going to say, or did you have something else to add?
I was gonna say the same thing.
Exactly right. The vacuum sealer means it's mostly devoid of air. There's no air. All right. I think instead of me reading this, what I should do is actually go to an X-ray tube so you can see, so I can talk about it. And then, yeah, let's use this one. When you apply a current to the tube, the filament heats up and then it releases electrons. You can see them right here, right? We get a little pencil. You can see the electrons that are released from the heated filament. What do we call that process? Does anybody know?
Thermionic emission.
Thermionic emission. Fantastic. So then, and the electrons that are accumulated around the filament, we call that a space charge or electron cloud. Make sure you know that. This is before they're accelerated. Now remember, this all happens really quickly, right? By the time you half press that exposure button, the anode starts to rotate, and then you finally press it, then the electrons are released and accelerate towards the cathode, towards the anode. So again, thermionic emission, proper definition is the release of electrons from a heated source. What happens in the X-ray tube? Electrons crowd around the filament, and we call that a space charge or electron cloud. Make sure you know this. Make sure you know this. The space charge is limited. If you think of it like an elevator that usually has max weight. It can't take a lot of people. It will tell you, the fire marshal will say 20 people at max. So it's limited to about 1,000 or so milliamps. That's the limit of how many electrons can crowd around the the filament.
What's the limit? 1,000 what?
Milliamps. About 1,000 milliamps. About 1,000. Some tubes have a higher capacity. All right, so the anode, the anode and the filament are usually made of tungsten. It has a high atomic number, which is preferred, and a high melting point. Now, what does that mean to have a high atomic number? Does anybody know?
Does that mean that it's harder for well, in terms of like X-rays, I know that having a higher atomic number means it's more dense, which means that it has lower or lower attenuating properties.
Or that would be the other way around, but it is more dense. Conan, what you got for me?
Because it has a high atomic number, it can have more interactions, which can create more X-rays.
Oh, let's go. Let's go. That's exactly right. So a high atomic number on the anode side where the electrons are bombarding, that means it will have a higher chance of having interactions to create X-rays. So more efficient in X-ray production. Fantastic. Fantastic. So if you think about this, right? Let's say this is the nucleus. It's really, really dense. Versus one that is not so dense. That's some of the material. When the electrons come over, I'm going to draw the electron in red. Say we have a bunch of electrons coming from where, Layla? Where the electrons coming from? What side of the tube?
The cathode?
Fantastic. So imagine if this is sparsely populated, there's a good chance we won't have any interaction. Hence, we won't get any X-rays. No X-rays. But then if it's densely populated, same electron coming, there's a greater chance or greater probability of some kind of interaction, and then we would get X-rays. This is why we prefer tungsten as a material for the anode. What about high melting point? Why would that be relevant? Why would that be relevant? What do you got for me, Alan?
The high melting point for the tungsten is I'm gonna guess is just how high the tungsten can heat up until it melts. I'm just guessing.
Yeah, you pretty much say it, but let's see if Regina has anything else to add. What do you got, Regina?
It increases essentially the possibility for thermionic emission.
Yeah, for sure for the cathode. And what about the anode? Why would we want that to have a high melting point? Regina, I'm gonna stick with you. 1 second, Sarah. Oh, Sarah hasn't answered this whole time. Let's go, Sarah. What do you got for us?
So it doesn't burn?
So it doesn't burn, doesn't vaporize. It still happens. We'll talk about it in just 1 second. Right? So you want a high melting point. Now imagine if the tungsten was a material that melts easily. Say it was made of plastic, God forbid. Every exposure, you'd have to change the tube. So it's not good. So we want to have a high melting point. All right? Um, we'll talk about the focal spot and so on and line focus principle in just a bit. I think those are best explained when you have a picture on the screen. Go ahead. Sarah, you got a question or was that your hand, a residual hand raise?
Oh,
Good.
I just looked it up.
Okay, got you. So let me go back here. So let's go. X-ray tube failure. So just remember, I'm not ignoring this. I'm going to go through it, but when we have something on the screen with an actual picture. All right. X-ray tube failure. Most common cause is excessive heat. And so you apply a high exposure to a cold tube, that kind of stuff that can cause it. Arcing is another cause for tube failure, right? So arcing just means let me see if I could draw this. Give me 1 second. Here we go. Make sure you know this. Sorry, the most frequent cause is abrupt failure. Abrupt failure is arcing, but you can damage a tube over time with high exposures. But let's say arcing. What's happening with arcing? And you've probably seen this with the Tesla tube. Have you guys been to a science fair or a science museum where you see them have this Tesla coil that has the electrons? Anybody seen that? Especially in Boston. Anybody seen that? Sounds really, really loud. All right, Alan, you've seen it. Are you nodding your head? Are you chewing? I think you're chewing. I don't think he's.
I seen it on YouTube
Oh,
from
you've seen it on YouTube.
yeah.
Got you. So we prefer if electrons are only going from the cathode to the anode, and it's attracted to the anode because, well, opposite charges attract, right? Now imagine if bits of the anode, which is positive, break off or vaporize in other parts of the glass envelope, then the electron would also be attracted to these parts. And that's what we call arcing. That's instant tube failure. Instant tube failure, right? So let me bring up a picture. It won't be tube arcing, but it will explain what I just said. So we prefer electrons, these are electrons here, to go from cathode to anode. But imagine bits of the anode have then broken off or vaporized and are now stuck here on this part. Electrons don't care. They're just going to go where they're attracted. So instead of heading towards the anode, they will now be attracted to the bits of the anode that are on the sides. And that is the explanation of arcing. And that's the cause of instant tube failure. You hear a loud banging sound and you gotta shut the machine off, or it will shut off itself. You gotta get a tube immediately replaced. Usually happens with older tubes or tubes that are close to or at the end of life. All right, so the question was most common cause or what can cause instant tube failure? Arcing. What's arcing? When bits of the anode have peeled off or vaporized, and then electrons are attracted to that part of the anode and it's going where it shouldn't go. All right. The other thing that you should be aware of is you should make sure you warm the machine up every day. That's usually done by the first shift tech or the overnight tech. But in any case, it's only necessary if you haven't used the machine for a long time. And in today's society, these X-ray machines in most facilities are constantly being used, unless you're in an outpatient facility or an urgent care where they shut it off overnight. In which case, you got to do a warm-up procedure. Otherwise, you can damage the tube by using high exposures on a cold tube. Think of it like It's a sudden temperature change. Imagine you get, you know how they say you shouldn't put your hot food in a glass, in a cold glass bottle or something. Then that sudden temperature change can cause it to break. It's not dissimilar to what can happen to the anode or to the tube. If it's not warmed up gradually, and you expose it to a high heat or high exposures, that can diminish the life of the tube, right? Again, this is done by the first shift tech or the overnight tech. Machines that are constantly being used do not need to be warmed up because they're just the heat is constantly maintained by each exposure. You should never use a maximum technique. I mean, don't think anybody's doing that anyways, but you should know this, to a cold tube. In times past, you would have to learn how to calculate the different heat units, or how much heat is generated at the anode. So I got a question for you. About what percentage of the kinetic energy? First of all, what's kinetic energy? Let me get Madeline. What's kinetic energy?
Kinetic energy is the like many electrons moving at a fast pace at one time.
Just in general, what is kinetic energy? Want to give it another shot? I see you, Cassandra. 1 second.
Just like energy moving.
Energy in motion. All right. Cassandra, were you going to say something different?
No.
Okay, so the electrons that are moving have kinetic energy, and most of that energy is converted to what? Um, who we got here? Vivian. Most of the energy is converted to what?
Yes.
Go ahead, Vivian. What do you say?
I said heat.
Heat. Fantastic. All right, so a lot of heat is generated at the tube. So in times past, you'd have to do a little calculation to find out how much heat was generated in a single phase and a three phase and so on and so forth. These days, the machine does it for you. In any case, I'll put one formula on here, and this single phase one, which is no machine uses single phase system anymore. This is just for reference. So even though the current machines use high frequency, this formula shows you that it generates more heat because we multiply the kV and the MAS by a factor of 1.4. So a single phase older system would generate less heat, less efficient. This one's more efficient, but it generates more heat. So if it generates more heat, it stands to reason we gotta cool the tube by a variety of ways, right? And fortunately for you, you don't have to look at these charts anymore. I'm going to show you real quick though. You don't have to look at these charts anymore, but there was a time it was on the registry. You have to understand what's a safe exposure, that kind of stuff. And just for information purposes, you have to look at this, and I won't go through all of it. You have to look at it to see how much heat units. So for example, they would say an exposure we've used an exposure that includes, say, let's do 200 kV at 200 MA and at 0.4 seconds. And then you'd have to go up here to see how long it would take for it to cool down so you can make another exposure. Well, you don't have to do that anymore because the machine does it for you. And it will tell you you can't use that amount of MA. Basically, it's using some kind of chart on the inside to tell to limit damage to the tube. You no longer have to do this. We used to have a chart that's on the wall that you'd have to look at to work out, are you damaging the tube? Are you making a safe exposure? Full disclosure, none of us cared. We just pressed the button. But this is something that we needed to do. But your machine does it for you. You don't have to do it. This is just here for informational reference. You never have to do this at all in clinic. All right, so how then do we keep the tube cool? Right, so I gave you a little taste of this stuff earlier on in other PowerPoint, but there are a couple ways that we cool the tube. One is by conduction, the other is by convection, the other is by radiation. Pretty straightforward. So the anode conducts heat away from the site of X-ray production. We'll talk about it in a second. That's one way. So by conduction, which is how heat moves through solids. So heat is conducted away this way. That's one way we control heat in the tube. The other way is by convection. A lot of tubes have oil around the tube, around the glass envelope. And then so heat is moving from a point of high concentration to low concentration. So heat moves, right? Not cold, heat moves. And it's cooled by convection, the way how heat moves through liquids in this case. And then radiation, well, if you have a higher surface area with these coils, then it's going to lose heat that way. Think of how uh, uh, a fan cools you down, kind of thing. So heat radiates how heat moves through air. This is why everybody complains about the X-ray room being too cold, because we got to keep the room cold to cool the tube down. So again, the question will be, what are some ways that we cool the tube? Convection, conduction, radiation. Conduction by heat moving through the anode stem. Convection by the oil surrounding the tube, and radiation because we have to keep the room cool to cool the tube down. All right. So just to recap, we've talked about the the one part of X-ray production and how electrons bombard the anode from the cathode to the anode, and how heat is conducted away or radiated, or we use convection to cool that tube because 99% of the energy conversion is from kinetic energy to heat. All right. Another way we keep the tube healthy is by rotating the anode. So when you spin, you half press that exposure button. I think we spoke about this a couple weeks ago. You're priming the anode, so the anode starts to spin. And why would a spinning anode or rotating anode be more efficient than a stationary anode? Does anybody know? It should be revision, I think. Does anybody know? Go ahead, Henry.
It can dissipate the heat better if it's rotating.
Fantastic. And then we're not hitting the same spot all the time. Fantastic. So we spin the anode. So when you half press that button, I forgot who asked this question a couple weeks ago. You're spinning the anode. You actually hear it spinning. You're spinning the anode, getting ready to do the second stage of exposure, much like you do for a camera, right? And so then you might ask yourself, how do we spin the anode if the glass envelope is vacuum sealed? Let me find a good picture. Picture on here, 1 second. Beautiful. This one's good. Well, we use an induction motor, and that's how it's similar to how we transfer energy from one side of the transformer to the other. Well, we have to maintain this vacuum sealed environment for X-ray production, like Kennedy says, so no air molecules can interfere with the electrons coming from the cathode to the anode. But we also need to spin this. Well, the induction motor, make sure you know this, consists of basically two parts. Some would say three: bearings and a stator and a rotor. At a minimum, you should know it has two parts: a stator, which is stationary. Let's use this one, and a rotor which spins. How does it spin? With a magnetic field. So this induces a magnetic field because it has AC power, and it spins the rotor, which is stationary, the stator, which is spinning, the rotor. Pretty self-explanatory, I think. Rotor, R for rotating, stator, S for stationary. Which one's outside the glass envelope? What do you think, Rico? Which of these is outside the glass envelope?
I'm gonna say the rotor.
Uh, maybe I didn't hear you. Which one is outside the glass envelope?
Outside of the envelope.
Yeah, I didn't hear you just now. What do you say?
I said rotor, but
you can see the glass envelope here, huh? Take a look. You see the glass envelope.
you're
See
saying
it?
outside of the envelope, right?
Yeah. So you can see the glass envelope. See it?
Yep.
So this bugger here is outside the envelope. You see it?
I was looking at a different picture. My bad.
That's all right. Wait, which picture's on the screen? Can you see me drawing?
Yeah, but I have my laptop up with the.
Oh, I see. I got you. Just want to make sure I didn't have the wrong screen up. Okay.
No.
All right. So the stator is outside the glass envelope. All right. Rico, I'm going to stick with you. What about the cathode and the anode? Are those inside or outside the glass envelope? Are they outside the housing? What do you think?
Inside.
Okay, fantastic. Cool. All right. Which of these conducts heat away from the anode? Garcia, what do you think?
Which one of these conducts heat away from the anode?
Yeah, which part of this you think conducts heat away from the anode?
Away. Conducts heat away from the anode. So probably the negative charge.
No, it's a solid structure. It's labeled on here.
So probably the rotor.
The rotor. Yeah, you could say that. With the anode stem. Make sure you know this. The stem
Okay.
of the anode, because it's the only point of contact. Stem of the anode conducts heat away from the anode itself. All right, so just to recap where we're at so far, we identified that the cathode side is a negative side. The cathode assembly consists of the focusing cup, which is negatively charged, and the filament, which is also negatively charged. When electrons are released by thermionic emission, what did I say is formed here? Let me get 1 second. Let me get Jacqueline. What is formed here by after thermionic emission? What's that term I used?
I'm sorry, I had stepped away. I didn't hear that part.
Which part? The question?
The part where you mentioned what? Yeah, I didn't hear that part. I just sat down. Sorry.
Okay. Clunis, what do you got for me?
Is it the electron cloud?
Fantastic. Electron cloud. It has another name. What's the other name? Space charge. Fantastically. I see you. Excellent. Excellent, excellent. All right, let me close this. So nice done, both of you. Okay.
Could
All
you
right.
repeat the question that you asked just so I understand how it's gonna sound?
Sure. The question was, okay, what is formed here during thermionic emission? And so thermionic emission, as we said, was when electrons are released from a heated source. So we have a space charge or electron cloud that's formed right here. And that means electrons are crowded around, ready. If you watch Cloverleaf, they will show you a bunch of horses of electrons, electron horses. A little weird, but this is how they put it. Crowding around, ready to be accelerated towards the anode. All right, Cassandra, you got it?
Yeah.
Jacqueline, you got it? Okay, cool. If I'm speaking too fast, let me know and I'll slow down. Huh? Okay. Before we talk about the Heal effect and line focus principle, let me do some labeling practice. Let me get, I don't know if these other people are here. Phoebe, are you here? I'm not sure. It's okay.
I'm here.
Okay, awesome. What is this structure called together?
That's the filament.
All together, what do you call it?
Mm, I'm not sure.
That's all right. Does anybody know?
Is X-ray tube?
Mm-mm. So I am speaking. Go ahead, King. Maybe King has it. Let's see.
Cathode?
Cathode assembly that encompasses the filament and the focusing cup. This is revision for most of you, right? Is this familiar? Say yes.
Yes.
Okay, awesome.
Yes.
This is why I'm going at this pace because I want to get to the questions because I think most of this is familiar. So the cathode assembly, make sure you know this, includes the focusing cup and the filament. All right. What is this structure here labeled S? Let me get Dadiak, are you here? I'm not sure if Dadiak is here.
Yeah, I'm here.
Got you. What is this structure here labeled S?
The statue something.
Hmm?
The
Again.
statue, I can't pronounce it. The statuary.
I promise you can. Stator.
Stator, excuse me. I just got a quick glimpse of it. That's why I didn't.
That's okay. But I'm gonna help everybody to get this stuff. Stator. 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 What does that do? Why is that important, Dadiako?
That's what cools it's part of the fan that cools down the electrons coming out from the anode. I mean, it's part of the heat dissipation from the anode casing.
Phoebe, what do you got for me? Listen to this, Dadiako.
I'm pretty sure that it just provides the energy for the rotor to have the anode rotate.
That's exactly right. Anode rotates, right? So it spins the anode with a magnetic field. How does the anode spin? The stator creates a magnetic field to spin the rotor. Why is the glass envelope vacuum sealed, and what does that mean? Crystal, are you here? 4, 3, 2, 1. Lee, are you here?
Yes, I'm here.
Oh, I meant Christian Lee. So sorry.
Oh,
All right, you know, I'm gonna go with the mainly the people who I can see because I don't know if the others are here. So I gotta respect the others who put their cameras on. So let me see. Kennedy, what do you got for me? Why is why did you say the glass envelope is vacuum sealed?
Because to prevent any air molecules from interacting with the electrons.
Fantastic. Madeline, what's one function of the tube housing? Madeline.
The tube housing, isn't it to like help protect like the glass envelope
Yes,
or the
so
cathode and anode?
anode, right? Anode.
Anode.
Anode. That's okay. Phoebe's got it. Phoebe wants to give you the alley-oop. What do you got, Phoebe?
I think it prevents radiation leakage as well.
Sure. Fantastic. One more, Rico. What do you got from Rico?
So we don't get shocked,
So you're
electric
going,
shock.
yeah, exactly right. So you don't get shocked, right? Because the electrons flowing there, and then not all of it is absorbed by the anode, right? All right, cool, fantastic. What are 3 ways that we cool the X-ray tube? Let's see what we got here. Raul, what are 3 ways that we cool the X-ray tube?
Uh, the anode stem,
Anode stem, what does that do?
it attracts all the heat away from the anode.
Fantastic. Tell me 2 more ways.
That's a good question, Professor.
It is a good question. All right, that's all right. That's okay.
Sorry.
There's no need to apologize. That's why we're here. It's class. Jacqueline, what do you got for me?
Keeping the room cold,
Yeah.
cool,
Uh-huh.
and the oil that surrounds the tube,
Cool.
that's in the tube.
Nicely done. So the first one I mentioned was radiation. The second one was convection. Regina, you got a question or a comment?
Question.
Mhm.
So when we mentioned that the anode conducts the heat away, that's by means of the stem. That's what's doing that, the conduction part.
Yes.
Gotcha.
Yeah. I think that was Garcia's question a couple minutes ago. Garcia, you understand this reference?
Yes, sir.
All right, cool. So that's a review quick so far of what we just looked at. Now let's look at some other stuff. So line focus principle. And you've heard these terms before, I'm pretty sure. Before I get into the discussion, does anybody remember what the line focus? Let's start with the easier one, I think. Anode heel effect. Does anybody remember what that's about? You can just put your hand up. Oh no. Oh yeah. Clunis, what do you got for me?
It's how part of the anode absorbs some of the X-rays. So between the cathode and the anode, the beam intensity is different. So it's like it's more penetrable on the cathode side than the anode side.
Fantastic. Or higher intensity, we want to say, right? Higher intensity. We have a higher intensity, not penetration. But yes, nicely done. Phoebe, you got a question or a comment?
Oh no, she answered it pretty well.
All right.
It's got to do with the geometry of the anode, I think, right?
Anode. Don't worry. Every time you say it wrong, I'm going to correct
Anode.
everybody. Anode. That's okay. This is what if we're in class. This is what we do. Anode, no I. Anode. That's exactly right. So just remember, it's intensity, not penetration, but intensity. And so, which part of the body? Let's say you are now doing. I'm going to draw something on here. So it looks like I can just go to questions rather than discussing this thing because this is largely familiar for you. So let's imagine you're doing now in theory, because in truth, full disclosure, these modern machines, it doesn't matter. but this is all in theory, right? So let's say you're doing a body part that looks like this. So this is obviously the thicker side. Which side should you position under the cathode? Chris, don't answer. Uh, uh, Phoebe's got it already, it looks like. Wait, Miss Cassandra. Give Cassandra a shot. What you got, Cassandra?
You should place it towards the thicker side, which
Got
is
you.
the hill. You should place it more towards the hill because it's thicker, and since the cathode, there's high intensity, it'll allow for even like distribution of the heat or X-ray.
Of the X-ray, of the exposure
X-ray.
to the IR. And just to correct, every time you say it, I'm going to say it a different way. Cathode, not an anode. No I, right? There's no I here. Chris, the reason I said I didn't answer, in a review of a couple months ago, you think you said fat cat. Was that you or somebody else? Am I mistaken this? Was it you? I think, was it last year in November?
Yeah, that's definitely
Yeah, yeah.
something I remember it.
Yeah. Is that, Raul remembers this? Raul, you remember this? Yeah, fat cat. Who taught you this stuff? Anyway, it's like fat cat. Is that a thing that's,
Mr. Ba.
that's
Professor
about?
Ba.
Yeah, that's pretty cool. All right, cool. Um, All right, so that's the anode Heal effect. This just means the beveled edge of the anode absorbs part of the beam. So it stands to reason if we have if the angle changes, then the anode Heal effect will be more pronounced. There is another picture I'm going to bring up in a second. What about the line focus principle? Does anybody know what this means? Line focus principle. Go ahead, Cassandra.
I think it has something to do with like the angle. It has something to do with like the effective focal spot being much smaller than the actual focal spot, which allows for like better spatial resolution because the target is at an angle.
Oh, beautiful. It's a nice segue into the difference between these two. I'm going to stick with you, Cassandra. What's the difference between the actual focal spot and the effective focal spot?
The actual focal spot is where the electrons hit, and the effective focal spot is what interacts with the focal spot, like what interacts with the actual IR. I don't know, something like that.
Something like that. Phoebe, what you got for me?
I thought it's the opposite. The actual is like the actual size, and then the effective is the size that the angle creates. So the effective is smaller than the actual.
I see. All right, we're going to clear this up. By the way, you're not having a seizure. I'm actually doing this on purpose. All right, so on this slide, you can see the difference between the two. The actual focal spot, make sure you know this, is the part on the anode where the electrons make contact. So the part of the anode where electrons are bombarding it. That's the actual focal spot. So this bit here, let me get my little pencil. This bit here is the actual focal spot. The effective focal spot is the X-ray beam that's projected downwards. You know the difference. This is the actual focal spot. This is the effective focal spot. All right, so if you were to put this in your own words, does anybody want to say it a different way? Uh, is there anybody that has a question about this? The difference between the two. Is this now clear, Cassandra and Phoebe and everybody else? All right, cool. So then the anode angle of the anode affects the effective focal spot. You can see a larger angle gives you a larger effective focal spot, and a steeper angle gives you a smaller effective focal spot. So these two are directly related. Directly related.
But I thought a shorter SID affects the anode field effect as well.
But this one we're speaking about the line focus principle. We can go back to that in a second.
Okay.
Right? All right. Just a line. Thank you for saying that though. But the line focus principle, you should know that the anode, the angle of the anode beveled edge is directly related to the size of the effective focal spot. Larger angle, larger effective focal spot. Smaller angle, smaller effective focal spot. What's the difference? The actual focal spot True or false is the photons that are hitting the anode. Is that true or false, Kennedy? Actual focal spot is a part of the anode where the X-ray photons are making contact. What do you think, Kennedy? True or false?
Can you repeat it one more time?
Sure. The actual focal spot is a part of the anode where X-ray photons are making contact. True or false?
True?
No, false. Electrons are making contact. Be careful, not photons.
Okay, wait, can you repeat the question again? I'm
Sure.
getting.
True or false, the actual focal spot, this bit here, is a
Mhm.
part of the anode where X-ray photons are making contact.
Oh, okay.
Is that right? That'll be false. Electrons are making contact here. All right? Because, make sure you know this, the anode is a source of X-rays. All right?
So
Which,
just to make sure,
yeah,
the effective focal spot would be the X-ray photons.
yeah, that's
Okay.
projected downwards. Yep. Effective. Effective focal spot. All right. So I think we have the gravy for this question here, which is what are the conditions necessary for X-ray production? Now, we've talked about all of them, believe it or not. We have. We Ming. Oh, you can't talk. I think you're in the library, so we'll let you stay. You can type your answer if you like. Conlon, what are three conditions necessary for X-ray production?
Three conditions necessary for X-ray production.
Hmm.
Well, a source of electrons,
Which is?
the filament,
Yeah,
a place to receive the electrons, which is the anode.
yeah. A way to decelerate them, that is, right? But yes,
Yeah,
sure.
decelerate them.
And one more.
And a vacuum for them to pass through.
Some books say a vacuum, but it's not necessary. It just makes it more efficient. But one more.
Um,
I'm gonna stick with you.
I would say an exit point.
No, I'm gonna stick with you. How do we get the electrons to go from the cathode to the anode?
Fermionic emission.
Mm-mm. How do we accelerate them?
Accelerate them.
Don't worry. That stretch you feel is your brain growing. It's a good feeling. Accept it. I'm gonna stick with you, Colin. Giving up?
Yeah,
That's all right. Don't
unfortunate.
don't worry about it. Chris, what you got for me?
Potential gradient.
Potential gradient. That's one way to say it. Alan, what are you gonna say?
I was gonna say something similar. I don't remember the word, but it's something to do with kinetic energy.
Not quite. Tasha. Tasha hasn't spoken up this whole time. Let's go. Tasha's got it.
I would say high voltage.
Voltage. Voltage. We need voltage, right? So you apply the current to give you the thermonic emission, then you apply the voltage to accelerate the electrons because voltage is the electrical potential difference, right? Or electromotive force. Sounds good, Conlon? Good?
So the three steps
Yeah.
are the high voltage generator, the film. Wait, can you just repeat it, please?
Sure, absolutely. The question was, what are the conditions necessary for X-ray production? The first one was the source of electrons, which would be the cathode. And he said it in this order, but it doesn't matter. But I prefer this way. The way to accelerate the electrons, which is the voltage, and a way to decelerate the electrons, which is the anode. Some books have a fourth, which would be a vacuum environment. But it's not necessary in my view because you can still have X-ray production, it just won't be efficient. In any case, if you see that as an option on some kind of a question, include the vacuum. If you don't see it, select those three. Sounds good?
Yeah.
All right. Cool. Cool. How come I can't? Okay, here we go. All right, why don't we take a 10-minute break because this is a short one, and then we'll come right back. We didn't take a break the last time. 10-minute break. So I can rest my voice a little bit. We'll come back in about 10 minutes. So it is 10:22. Come back at 10:30, 12:32. I'll stick around for those who have questions. So All right, let's continue on. Give everyone 15 seconds to get back. All right, so we've spoken about the condition necessary for X-ray production. We've spoken about the cathode and the anode and how the anode spins. We've spoken about the glass envelope and why it's vacuum sealed. We've spoken about the material makeup of the cathode and the anode and why we choose a high atomic number material and a high melting point material. Now let's dig in a little bit more into the cathode assembly. The cathode assembly consists of the focusing cup and the filament. Now, almost all, if not all, the industry standard right now is dual focus tubes. What that means is that there are two filaments, a small one and a large one. Before I go on a little, excuse me, rant about this, does anybody remember the usefulness of either of these? Small focus spot and a large focus spot. Does anybody recall? Go ahead, King. What do you got?
A small focus spot is used for better detail.
Excellent. What's the disadvantage of using a small focal spot?
Blanking.
Oh, you're blanking. I got you. I got you. No worries. I
Yeah.
got you. I thought that was a disadvantage. I'm thinking, what? Never heard of that one. Alan, what you got for me? Alan's gonna give you.
The disadvantage for the small focus filament is that it doesn't dissipate heat as much as the large.
Yeah, so we had a lower heat capacity. I mean, you got to use a lower MA setting. Phoebe, question or comment?
A question. Do they have something to do with penumbra as well?
Oh God. We will talk about this unless you already have in image production.
Yeah.
But yes, so you probably talk about that then. But yes, it does. I would not mention it here. No, I'm just talking about the equipment specifically. All right. So
Okay.
this is why I didn't talk about SID and so on, because that has to do with imaging. But just equipment related properties, the small focus spot give you better detail for sure. But as a consequence, you can't use high MA settings. And the reverse is true. So if we want to use a high MA setting, let's say for a larger body part, say the abdomen or so, then the larger filament is selected. Fortunately for you, you don't have to consider any of this. The machine does it for you. By the time you go in and you select hand or you select chest or abdomen, the machine has decided which is the best option. All right, so you don't have to do this, but you should be aware that the industry standard for X-ray tube design is that of a dual focus tube. That means we have two filaments, one small, one large, in the cathode assembly. Any questions on this? I think this is easy review. This is clear for everybody. Okay, awesome, awesome. So I think now we can get into just some questions. Kind of the same. See, I think we've covered everything. This is a short one, really short one. I actually struggled to find 70 questions for the upcoming quiz. I really did. But I did it. So you can expect the same question but asked four different ways, kind of thing. Oh, all right. So this we haven't spoken about. So earlier we talked about how to make sure we're operating the tube in a safe way. We gotta warm the machine up. Sometimes you can have tube damage by vaporization or pitting of the anode. That just means we hit the anode with too much exposure when it's cold. This is a rotating anode. You can see it because there's a track of the anode spot. So even though you see of the focal spot, even though on here you see It looks like one little spot is actual focal spot. In actuality, because we are spinning the anode, it's actually a circle on the anode. Does everybody understand that concept? It's not really one spot because it's rotating, right? Think of it like you're walking in the park, but now you made a track through the woods. Well, this is a track, the anode track, but that's a focal spot. So if you hit this with too high of an exposure on a cold tube, you can have vaporization or pitting of the anode. That can damage the tube. Once it pits and we have bits of the anode that's lodged on the inside of the glass envelope, then we can have arcing. What's the consequence of tube arcing, Madeline? It's a consequence of tube arcing. What happens?
I'm not sure, but I just see on the screen it says flashing of current in the wrong direction.
Well, that's the definition, but what happens to the tube? Does anybody know?
Hmm.
Looks like we got Alan. What do you got for me?
From what I remember, you said is because bits of the pieces of the atoms have been ripped off.
Yeah, sure, but what happens to the tube? Does it make it more efficient, less efficient?
No,
Does it stop
it's less
working?
efficient.
So it's tube failure.
It's
Make sure you know this.
oh, tube failure. Yes, you're right.
Tube failure. Instant tube failure.
When you explained, you said it bits of the anodes are ripped off, and what happens?
It's lodged on the inside of the glass envelope.
Okay.
All right.
What is that? What you said?
The anode is vaporized.
Oh, okay. All right. Thank you.
All right. The anode is vaporized. That can happen. So we have bits of it that are broken off. These are minuscule parts, but enough to cause the electrons to flow in the wrong direction. All right, so we can also have the filament that's vaporized. So if you remember the old style bulbs, I think I talked about this in a review, guys. Review with you guys some time ago, and you would shake it to tell if the filament, if the bulb is still good, right? You guys remember? Anybody remember this? No? See me? Am I dating myself? All right. So there was a filament actually inside, much like the filament we use for the cathode side of the X-ray tube. And if that's broken, then no current will flow, right? So if you try to take an exposure and there's no exposure, it's probably something devastating has happened to the tube. Or it could just be an alignment thing where if the tube is not aligned to the bucket, some machines wouldn't allow you to expose. But we're speaking of equipment design here, and if the filament is vaporized or the anode is vaporized, we can have no exposure, or we can have tube arcing that causes tube failure. Sounds good? We good? Any questions on this stuff? All right.
Question, Professor.
Yes, sir.
Difference between arcing and pitting.
Arcing is when the electrons are attracted to other parts of the tube where bits of the anode has lodged. And so we have electron going in different directions. That's a problem. Pitting just means, like you can see here, bits of the anode have been, peeled away. All right.
Thank you.
You're welcome. All right, so question. Where would you find these tube rating charts? Jacqueline, where would you find these tube rating charts? When you go to clinic, where do you find them?
I thought we don't use these anymore.
Oh, there you go. You're getting used to my trick questions. You don't use these anymore. That was something that's quite archaic. It would be hung up and you'd have to look at them and determine when it's safe to make an exposure so you don't damage the tube. All right, so let's do some questions here. Let me go up here to some questions. What is thermionic emission? Let me get Rico. What is thermionic emission?
Is that the electron cloud, the buildup of electrons
Yeah. So
at the
So we
cathode
would
side?
say the release of electrons from a heated source. Make sure you know this, just like that. What's the difference between the actual and effective focal spot? Let me get Layla. What do you got for me?
Okay, so the actual focal spot is where the electrons bombard the anode, and the effective focal spot is like kind of like a continuation of the electrons going that are being projected like through the central ray. to my understanding.
Just to be clear, once there's a bombardment of the electrons onto the anode, we now have X-rays. So that's the conversion right there. So you meant the
Right.
X-ray photons that are projected down. I think that's what you meant.
Yeah, that's what I meant. Yeah.
Okay, cool. How is the anode beveled edge angle, or the angle of the anode, how does that impact the effective focal spot? Who else has a camera on? Let me see. Vivian.
I'm actually not sure about. I think one of them gets smaller based on the angle, but I don't remember the relationship between them. I know there's a diagram on the screen right now, but
That's all right. This is why we do
I
this
think
review
it
part of it.
gets.
Oh, you gotta give it a shot. Go ahead.
I'm gonna give it a shot. In the diagram, it looks like the effective focal spot size is smaller than the actual one, but I don't know if it's because the angle is bigger or smaller, and it's because the angle's small.
You're getting so close. I'm gonna stick with you. We have time. I see you, Phoebe. 1 second. I'm gonna stick with you. I know. I see you holding your head, but we can do it. We can do it. So
Walk me through it.
you have to now say to me to take a look at the image, and as
Mhm.
one gets smaller, what happens to the other one? And then what can you say to describe that relationship?
As the angle gets smaller, the effective focal spot is smaller than the gets smaller than the actual focal
Don't
spot
drag the other one in.
size.
Just the relationship between the
No?
angle and the
Oh,
effective.
when the angle of the anode is smaller, it decreases the size of the effective focal spot size.
That would be it. Say it with gusto. So then, how would you
I
describe
did
this
not have
relationship?
gusto. I wasn't sure.
All right. How would you describe
Uh,
this relationship? Last one for you.
is it directly related then
That's
if one
exactly
is
right.
getting smaller? Okay.
That's
Okay,
exactly right.
gotcha.
That's exactly
Thanks.
right.
I
Oh,
appreciate it.
yeah, you got it. So I'm not here to save
Mm.
the those who are already in the choir. I'm here to save the sinners, those who don't know. So if you're unsure, that's why I'm calling on you. So, all right, you can help others too. So don't think I'm picking on you. All right.
That's okay.
The
I feel helpful.
Okay, cool, awesome. All right. So I also want you guys to get used to describing these in the simplest way possible. And here's why it's important. You might, and I think I've said this before, you're in the exam, the registry exam, and you sometimes might reason yourself out of the perfect response because you're overthinking it and you're trying to use every term that you've heard that's even tangentially related to the topic. And then you pick the wrong answer as a consequence. So try to simplify things as much as possible. It's a principle called parsimony. It just means the simplest explanation is often the most accurate. So if you can't say it in a few words, then do you really understand it? Is my feeling. All right. So then the we can say succinctly the angle of the anode is directly related to the size of the effective focal spot. All right. What do you understand? Oh, I'm sorry, Phoebe. You had your hand up. Were you coming with a question, or were you trying to answer the one with make a comment?
Oh, I was trying to answer it.
Okay. Do you understand what we're going to say? Does that line up with what you were going to say?
Yeah.
Awesome. What do you understand about the line focus principle? Let me see. Nick Renda, what do you got?
I just joined, so I'm not sure what the question was.
I
I
got
just
you.
got finished with advisement.
No worries. It's the second one right there on the screen. Second
What do
bullet
you
point.
understand about the line focus principle?
Yeah,
Uh, isn't that the size of the focal spot relative to the anode angle?
that's exactly right. That's exactly right. Cool. Um, Before I pull up the Kahoot, got you. What is the induction motor and why is it used? Clueless. What do you got for me?
Um, the induction motor is used to, is it to rotate the anode?
Yeah, exactly right. What are the parts? I'm gonna stick with you, Clueless. What are the parts of the induction motor?
The rotor and the stator?
Got you. So what type of force is used for to rotate the anode? Is it electricity? Is it ultrasound? Is it what do you think? 1 second, Rico. I'm gonna stick with
Uh,
Clueless.
Is it electricity?
Magnetism. Make sure you know this.
Okay.
Magnetism. Magnetism. Rico, is that what you're gonna say?
Yeah.
Cool. Awesome. Magnetism. Which of these is stationary and which of these is spinning? I'm not sure if Chris Garcia, what do you got for me? Which parts of the induction motor, which part is stationary, which part is spinning?
So the stationary part would be the stators, and the spinning would be the rotor.
Fantastic. 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 How do we cool the tube, Garcia? I'm gonna stick with you. Everybody gets about 2 or 3 questions. What do you got for me? How do we cool the tube?
So the anode stem attracts the heat away from the anode.
What do you call that?
Um, what do we call that? I'm not sure.
That's all right. Conduction.
Conduction. Okay, by
Conduction.
conduction. Okay,
And in general, that's how heat moves through solids.
got it. So that's conduction. Induction is for the spinning.
Induction, yeah, is for the spinning. That's not heat. That's not method of heat transfer. That's just how we move the anode.
Right.
But we're speaking now of methods of heat transfer. There are 3 of them. You've talked about one so far. Can you tell me 2 more ways that we cool the tube?
So the oil bath and the oil bath and the I'm not sure about the third one.
That's all right. That's why we're
Oh, we
here.
keep the room cool. We keep the room cool. I remember.
Room cool, fantastic. So names of those in the order of how you mentioned them. The oil bath would be by convection, and then keeping the room cool is by radiation. Sounds good?
Yep. Thank you.
All right, cool. You're welcome. All right, let me see who's up next. Okay, beautiful. Uh, Someone on mute just now to ask a question? No, okay. Um, who else we got on here? Alan, what do you got for me? 3 conditions necessary. You can say 4 if you like for X-ray production.
So I said the three essential conditions necessary for X-ray. Is it the cathode and the anode?
Hmm?
Is it the cathode and the anode? And then the 3 essential conditions necessary for X-ray production. I know this.
1 second, TV.
3 essential conditions necessary for X-ray production. Won't you need the thermiotic emission first? Will be the first step or no?
Yeah, that's part of it. Yeah, but there's another way we can say it. Were you able to take notes when I was speaking, or was I speaking too fast? What do you think?
No, I got notes. I'm not trying to look at my notes, see if I.
I appreciate it. Okay. I'm gonna come back to you because everybody gets a couple questions, but let me give Phoebe a chance to flush this one out. Phoebe, what you got for us?
Um, I'm pretty sure like he got the first two. It's also an electrical potential or voltage. I don't know the correct wordage. And the fourth optional one is the glass envelope.
Kind of. What are the first 2, by the way, just to make sure it's clear for everybody? I see you, Tasha. 1 second.
So you need the target where the electrons are going, so that would be the anoid. Did I
Anode.
say it right?
1 second.
Anoid.
Anode.
And then you need
1 second. And
the
1 second. Anode.
anoid.
Anode. No I.
Anoid.
No I. Anode. That's okay. Anode.
Anoid.
Mm-mm.
Okay.
Mm-mm. It's all right.
No.
We'll pick it up after class. Anode. Anode. Not.
Anoid. No,
Mm-mm.
I'm
Oh,
still getting it wrong.
that's all right. It's a habit that people have because you're allowed to go unchecked. Not in this class. So
All right.
this is why I do it. All right. It's not to pick on you, but it's okay. Please proceed.
And then you need the source of electrons, so that would be the cathode.
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 There you go. Now do the other one for anode. Not right now. Tasha, were you gonna say something? Nicely done, Phoebe. Tasha, did you have a different comment?
Yeah, I was just going to say the same thing. It's just like a source of electron from the cathode, a source of acceleration, a high voltage, and a source of deceleration, an anode, and a vacuum tube.
Vacuum tube. Fantastic. Fantastic. So, was that Phoebe? I think it was Phoebe. Phoebe, you would obviously be able to find the answers on a what do you call it? On a quiz or exam. The reason I stress the pronunciation for you and everybody else who make the wrong pronunciation, including myself, is so you can be able to communicate properly or have useful conversations with others in the medical team, right? So this is the only reason why I stress this stuff. All right. Let's try the Kahoot, which then has, let me just make sure I covered everything first. I
Professor,
did.
the decelerating of the from the anode, when she said the vacuum tube, is that all together?
No, she mentioned the fourth. So the
Also,
deceleration of
there's
the anode
four.
was the third thing that she mentioned. You're speaking
Okay.
of Tasha, right?
Yes.
And then she said that a vacuum tube. A vacuum tube is listed as another condition in some textbooks, but
Okay.
in other textbooks, it's not essential. Because if you think about it, when Wilhelm Röntgen discovered X-rays, he didn't have all these. He was by accident, right?
Oh, yeah.
We just decided we now know that a vacuum sealed envelope makes it more efficient.
Okay.
All right. Okay. Yes, we covered everything. So I think we can now skip to. All right. So before I do that, actually, so if you notice, we're building a story here. We talked about the atom at the beginning. Then we talked about electrons and how they're the atom configuration with subatomic particles. Then we talked about a circuit in the basic form, a series circuit, parallel circuit. We moved from that simple circuit to the X-ray circuit as a whole that has a primary, secondary, and the filament circuit and so on. And so now we've zoomed in on the X-ray tube, the business end of this stuff. So next week or the next time you hear my voice on a recording, it will be about what's happening at the anode, what's really happening right in here. So we're going to look into X-ray production with Bremsstrahlung and characteristics and so on. And in my view, this is the order this is not spelled right. This is the order that yeah, I think is useful and has worked for decades that I've been doing this. All right, so and I'll save this and I'll have to re-upload this because that's not going to bother me because focusing was spelled incorrectly. Give me 1 second. Focusing was spelled incorrectly. Is it this one? No. Rad Physics. There's something else on here. That was out of place. This one. Now, will that make you fail the exam? No. Is it gonna bother me? Yes. That's the only reason why I'm doing it. Chapter 7. I'm gonna delete this one and re-upload the next one. All right. Free of typo. Now we're ready. All right, so at the top of this one, you would see the study guide, Rad Physics study guide. It opens up to another Kahoot. And let's do host live. Wait, what did it mean on save changes? It's fine. We have a whole 30 minutes to do this. I think we can get you the whole thing. I think so. Give everyone about 40 seconds to sign on. Ten more seconds. All right, so here's a study guide. It'll be a list of stuff that I I included on the quiz that's already made. All right, label and functions of the X-ray tube. So we're gonna do a little mental gymnastics. If you can, close your notes, and we'll try to do some memory. Okay. So I'm gonna ask. Let me start from the top left. We have Tasha. What are some? Let me two parts of the X-ray tube that we just discussed. What are their functions? 4, 3, 2, 1. I'm not sure if Tasha can hear me. In the interest of time, Regina King, what do you got for me?
The anode and the cathode.
What are those?
The cathode accelerate yeah, they accelerate the negative electrons to the anode. Okay, so the cathode is the source of the
Yep.
electrons, and then the anode essentially I, for lack of a better term, it receives the electrons and then you get X-ray production at the anode.
Yeah. That's it. That's it. I know it's tempting to keep going, but you're gonna talk yourself with a good answer. So that's correct. All right. So there are other ways you can say it. So it decelerates the electrons. That's another way you can say it. All right. Tell me two more, Kennedy.
The the filament and focusing cup,
Okay, sure. Together, what do we call that? Those two together.
the cathode assembly,
Excellent. What charges do those have?
mm, negative.
Negative. Why is the focusing cup negative, Kennedy?
Um, I don't know exactly. The only thing I know is that you want the electrons to be not attracted. You don't want them to, you want the like charges to repel and then the opposite charges to attract. So that's all I really know.
The first part sounds good. I thought you said you didn't know, but let's see if Cassandra can flush that a little bit. I'll come right back to you, Kennedy. Nice done. We'll see what else we can say to flush that
I
out.
would say you want the electrons to flow in one direction, so it has to be negative in order to flow to the cathode, to the anode side, sorry.
To the anode side. So we want to focus the electrons, and that's based on how charges behave when they're close to each other. So, like charges repel. So the negatively charged focusing cup, well, it focuses the electrons towards the anode. All right, Kennedy? It's another way you can say it. All right, so Regina already mentioned the filament or the cathode. So you got to give me one more label of the X-ray tube, Kennedy.
Um, I guess the protective housing,
Sure. What's a function of that?
to prevent electrical shock.
What else?
Um, I think I'm mixing it up between, is the lead casing also?
Part of the housing, yes.
Oh, okay. So it also prevents, I don't remember if it's called unnecessary radiation. Is that what it's called? I don't remember if it's called that or another term.
Another term. I'm going to stick with you a little bit.
Okay.
Would you like me to give you a clue?
Yeah.
All right. Okay, I got it. So imagine you are in a recording studio and you don't want your voice to get outside, or you're in a dark room processing photographic film like Garcia does. I don't know if he does his own film, but like people do, right? And you don't want light to get in. Is that helping you?
Radiation leakage.
Oh, look at that. Look at that. That makes me so happy. Makes me so happy. Nicely done. Radiation leakage. All right. So we'll talk about the amount in a little bit, but I think I put a slide on there that tells you the minimum it should be. Lee, you ready? All right. Can you tell me two more labels and functions of the X-ray tube?
The induction motor.
Okay.
It has the rotor and stator.
Mhm.
it spins the anode target to dissipate heat, and then the rotor, I mean the stator, it's to create a magnetic field to to make the rotor spin.
Nicely done. Excellent. Excellent. We'll have to circle back. I think we have enough questions to give everybody at least two. I'm going to keep going on left to right. Nakita, can you hear us? I'm not sure. 4, 3, 2. Raul, you're up. You ready? Okay, cool.
Yes, Professor.
Anode heel effect. What's happening there?
The degree of the angle of the anode determines how big or small the electrons are going to be dispersed.
Mm-mm. I'm going to give you another shot. Would you like a
Uh,
clue?
yes, Professor.
All right. So you remember on the screen I drew something. I actually intended to draw a foot, but somebody called it a hill. That tells you what my drawing skills are like. So do you remember me drawing that little blue triangle thing?
Yeah, the fat cat.
Well, that was Chris's thing, and I think you nodded in agreement. All
Yeah.
right. So that's a clue as to what the anode heel effect is.
Uh, so towards the cathode side of the X-ray photons, it's a lot stronger than the anode. So you would have to align the thicker body part to the cathode side so you could have an even disperse of electron.
All right. Very cool. Not electron though. Be careful. I'm gonna stick with
Oh,
you, Raul.
yeah,
I'm gonna stick with you. Just remember now that this will be the X-ray beam, and then I
X-ray
think
beam.
it was at this point when somebody said energy, but it's not the energy, it's the intensity that changes,
Okay.
right? So the intensity on one side is greater. The cathode side, like you accurately said, is greater than the anode side. Why is that?
Because of the angle of the anode,
What's happening?
it is depending on how much degree is it on the cathode side, it's uh how do I say this? It's traveling a lot closer packed together than the further side.
There's another way. Um, uh, I'm gonna come back to you in a second, okay?
Okay.
Vivian, this is just one of your questions. Can you help Raul out?
I remember saying too, the relationship is directly related between the angle of the anode and the effective focal spot, and in the way of I phrased it as like the anode heel, the angle of the anode, if it gets smaller, it also decreases the size of the effective focal spot, which is the spot that is where the actual X-ray that
All right, so
comes out.
just to be clear, we're speaking of the anode heel effect. I think you're describing the
This is
line
different.
focus principle. All right,
Sorry,
so I
that
can
was
clear.
what I remember doing.
That's okay. So we're gonna clear this up right now, Raul, and oh,
Mhm.
Chris has got it. Let's go
Oh,
with Chris.
Chris got it. Chris got it.
I'm going to say the anode heel effect speaks to the uniformity of the intensity of the beam. So because of the angle of the anode, it is less intense on the anode side than on the cathode side. And that's why fat cat applies, because you put the fat side on the cat side.
Got you. So what's happening to the intensity, the X-ray beam on the anode side?
It is reduced
Why?
because of the absorbed uh, electrons.
Not electrons, photons that are created. But that's the bit that we're
Oh,
missing.
okay.
Yeah, yeah.
Because
So
that's the point where the photons are created,
that's exactly right.
Yeah.
right? So from electrons to photons, and then those photons, some of them are absorbed by the anode.
That's exactly right. That's the ingredient we're missing, Raul. Are you clear?
Yes, Professor.
All right, cool. Vivian, did you have your hand up? Okay, cool. We're not done with you, Rahul. We're not done with you at all. What is the source of X-rays, X-ray photons? Is it the cathode? Is it the anode? Is it the stators
The source is a cathode.
of X-ray photons? That
Yes.
would not be right.
No?
The source
So
of X-ray photons is not the cathode. I'm going to help you with this. Remember just now, Garcia said the electrons are absorbed. That's why the intensity decreases. And I said, no, photons, because photons are created at the anode. So the question is, what is the source of X-ray photons? That would be the anode.
The anode.
The
Okay.
anode. Source of electrons is the cathode. Where photons are created, the anode. Do not miss this.
Got it.
You got it?
Yes,
I
sir.
promise you, if we have time, I'm going to ask you again. So write it down somewhere. Tattoo it on your hand, something. All right, I'm going to come right back. Vivian, you ready?
I'm ready.
All right, this is your time to shine. Line focus principle.
Line focus principle again? I
Yeah,
just said it.
I know. Life is like this. Lee is laughing. I don't know. She believes in you. She
I
believes in
know
you.
she believes in me. So there's like two types of focal spots, but I was focusing on effective focal spot size versus the anode heel angle relationship. It is directly related, and if the anode heel angle decreases, the effective focal spot size will decrease. Is there anything I need to talk about for actual focal spot in this, by the way?
Mm-mm. But not
No,
right
it's
now.
not. It's not part of this? Okay, because I
No.
was a little confused. Okay,
Mm-mm,
good.
mm-mm, mm-mm. Not at all. But since you ask, what's the difference
Oh,
again between the actual focal spot and the effective focal spot? We'll stick
I
with you.
think I know. I think actual focal spot is where the actual electrons with the cathode hit the target anode target, and that's like this. That's the size of where it hits, and after that, when it comes out, it is the effective focal spot size in which of the photons come out, and that's the size is different when it hits the IR or the patient or whatever.
Yep, that'll be it. I think you can recall this in your sleep now. I've asked you so many times. I think you
Yes,
can.
honestly.
Garcia, you got a question?
Would it be fair to say that the actual focal spot is the origin of the photon?
Yes.
Okay, thank you.
Yeah, exactly right. Jacqueline, you ready? What types of material do we use for the cathode and anode, and why?
Um, Tungsten.
Cool. Why?
Because it can withstand heat, high heat.
Cool. What else?
Um,
Think of the anode specifically. I see you,
the
Cassie. 1 second.
Molly. I don't know how to say that word. Um, I know it's tungsten and Molly.
I think you're trying to say molybdenum. What I'm asking you is, what's the other property of tungsten that makes it a favorable material for the anode?
High atomic number.
Okay, why is that important?
Um, it's for efficiency.
Very cool. I think you got it, Jacqueline. Layla, you ready? Oh
Yep.
no, are you eating? I can come back
No,
if you
I'm
prefer.
listening, yeah.
Okay, good. Um, Tube failure. What can cause tube failure?
Um, Tube arcing, is that what it's called? Tube arcing?
What is that?
It's basically where I think I think it's when there's scatter that hits the tube repeatedly.
Mm-mm.
No?
Mm. I'm gonna stick with you though.
Okay.
You can do it.
Mm, no, I don't remember.
All right. Would you like a clue?
Yeah.
All right. Give me 1 second. All right. You ever did this experiment where you put black pepper in water and then you put soap on your finger?
No, I
Black pepper
haven't
sprays.
conducted that
You haven't
experiment.
done that? That's
No.
so cool. You should do it. Don't waste your parents' black pepper though. But I don't know. Jacqueline has done it multiple times. That's why she's got no seasoning in her cupboard. But so I'm gonna. Jacqueline, you've done this, right? You have apparently. All right. Let me think of another example. Give me a second, Lila.
Professor,
Yes, sir.
I'm curious about the same thing. So I'm just wondering, where is the actual arcing happening? Like when I think arc, I think of an arch. So is there something about this where there is an arc?
Ah, I see. I'm going to answer both of these. First, I'll think of an example, and then I'll show
Okay,
you a picture, okay? Give me 1 second.
thank
You're welcome. All right, I got it. So Layla, imagine, okay, I'm going to give an example. So yesterday I was driving with my kid on the road, right? And we're talking back and forth, talking about a story. And in the middle of this conversation, sometimes I'm very juvenile, so shiny things they distract me. So then I saw this thing on the side of the road. I said, "Oh, oh, look!" And then, I got attracted to this thing on the side of the road. So then my attention went where it shouldn't have gone, right? Okay. So the reason I'm bringing this up is ideally we want the electrons to flow from where to where. Think of that, my attention. Where should it go? Where should the electrons go?
From cathode to anode.
Okay, fantastic. So with arcing that can cause tube failure, it's going elsewhere because why does it go from cathode to anode?
Because it's going in the direct, like it's a direct current, so it's going from one place to another in one direction.
Got you. What are the charges of these two things?
Of the cathode and the anode.
Yeah,
The cathode is negative, the anode is positive.
which stands to reason if we have another positive element anywhere else aside from the anode, electrons would now be attracted to that thing. Sounds good so
Mm.
far? So then bits of the anode peel off and they're off to the side. And then electrons now, instead of going in a straight line, they arc, Chris, towards where it shouldn't go. Sounds good
And
so
that,
far?
yeah. And is that due to pitting? Why
Pitting
the,
of the anode,
yeah.
right?
So then it ends up in other places.
That's exactly right. Like the
Okay.
juvenile I am sometimes, um, what do you call it? When I'm talking to my kid, um, um, 1 second, let me be careful what comes up when I do this. Google is so weird.
So pitting leads to arcing.
Yeah.
All right, thank you.
You good? Or you would like to see a picture still?
Oh no, that's perfect. I get it. I see it.
Okay. All right, cool. All right, I think we're good then. Let me see. Go back here. All right. And Layla, you good with that? You good?
Yeah, that makes sense. Thank you.
All right, you're welcome. Fantastic. All right, we're not done with you yet, Layla. We're gonna keep going. Where were we? Tube Layla. What can we do to extend the life of the tube as technologists? What can we do?
I guess just like regular maintenance of the tube.
You will never have to maintain the tube, but there are things that you can do and do not do to extend the life of the tube. I see you, Jacqueline and Raul. 1 second. You're unsure, it's fine. We're in class. It's okay.
No, I'm not sure.
That's okay. Let me get Raul and then Jacqueline. What do you got?
I was gonna say, just warm up the tube.
Fantastic. Jacqueline, what can we not, what are we ill-advised? What's ill-advised?
To do send high heat to a cold um, anode.
Fantastic. Fantastic. All right, so before I do that, Layla, even though she didn't answer all the questions, she said something very, very important. And she said the tube kind of functions like a direct current kind of principle. Remember this, Layla? That's fantastic. And this is important because on some registry type material, I have to always use that caveat. They would ask if the X-ray tube functions like a rectifier. True or false? What do you think, Layla?
That what functions like a rectifier? The
The
X-ray
X-ray
tube?
tube, yes.
Mm, the X-ray tube itself?
Yeah. Oh, wait. Maybe I should ask this. Do you recall what a rectifier is?
Yeah.
What is it?
It converts AC to DC.
Okay. In other words, current is only flowing in one direction. So, in other words, does current flow in one direction with the X-ray tube or back and forth?
It flows in one direction.
Oh, therein lies your answer. So we
So it
could say, I'm sorry, go ahead.
does. So it
So
does
it,
act as a rectifier.
so it does. So it does. You could say an X-ray tube is a type of rectifier, or what's the other name for a rectifier? I promise. This is the last one for you, Leila.
A diode.
Diode. Fantastic. I think you're ready to get a 99% on this quiz,
I think
right?
so. I have a question though.
Let's go.
Okay, so if the X-ray tube itself could be considered a rectifier to act as a rectifier, then, and I may be jumping ahead, but I see on the slide it says what part of the X-ray system functions like a diode slash rectifier.
That'll be it.
It would just be the whole X-ray tube.
The X-ray tube.
Okay.
That'll be it. That'll be it. Remember, there are only so many ways that we can ask you. That means the ART and myself about radiography. So it's going to be just said the same question four different ways. The same thing for the registry. So if you know the material, it doesn't matter how they ask it. So then what's a diode? Rectifier. What's a rectifier do? Current only flows in one direction. Well, what other part of the tube, other system, allows current to flow in one direction? Well, the cathode to the anode, the X-ray tube. Sounds good? All right. Did I jump anybody? Oh, the names got mixed up. I think Lee, you're up next. I think. Did I get you already, Lee? I think I did, you know. Lopez, you ready?
Yeah, go ahead.
All right, cool. Why do we need an induction motor?
An induction motor is the motor, so the anode can rotate.
Cool. Well, why don't we just connect a wire to the and to a motor inside the glass envelope?
A wire
Yeah.
in the glass envelope? I
Yeah.
don't think that's physically impossible because it has the components in the tube, which is a cathode and to anode.
I think you're on the same right track, but let me just help you right here because
Okay.
we don't want to compromise that glass, the vacuum glass envelope.
Okay.
All right. I'm gonna get you one more
All right.
because I think Lee already mentioned the induction motor, so I gotta get you one more, okay?
Okay.
Wait. Oh, which part of the X-ray tube is the source of X-rays, and which part is the source of electrons?
The source of electrons is on the focusing cup, with it's included with the filament, which has two, a small and a large.
Okay.
And then the other question was, you said what was the other question again? I'm sorry.
It'll be the third to last bullet point on the screen.
Third level, electric source and electric source. Electric source, electron source. So I know it gets heated up and then it accelerates to the anode side and it creates with the photons, and then from the photons comes out the window port.
Just be careful. As simply
Okay.
as possible. Which part of the X-ray tube is where X-ray photons are created?
Oh, and
I'm sorry?
where X-ray photons are created from the
Yes.
anode.
There you go. Just like it.
Okay.
X-ray source. That's the same question, said a different way. All right. The reason why I try to make these questions, I think I heard someone say that the questions seem strange. The reason why the questions are put that way on the quiz is I don't want you to expect these things or to anticipate the wording because on the registry it's gonna be different. So I try to ask him in unconventional ways, so you got to think about it. So you might be thinking I'm going to ask you something that is verbatim what's on the PowerPoint. Sometimes it's like that. I try for it not to be like that, right? So it might say X-ray source or where X-ray photons are created. That's saying the same thing.
It will both be the anode, correct?
It will both be the anode.
Okay.
All right. If you, hopefully you guys are picking up on this pattern. We're keeping this stuff as simple as possible. So hopefully it's you can see the story that we're building. All right. Let's see what other questions we have. Everybody should get these right now, I think. Oh no. All right, we got one answer for all of these will occur. We got one answer for X-rays are released and accelerated towards the anode. Why is the green one wrong? Let me get Ashley Henry. I haven't heard Ashley this whole time. Let's go,
Um,
Ashley.
because it wouldn't be X-rays, it's electrons that are.
Fantastic. Fantastic. So then if green is wrong, that means obviously the yellow one is wrong. Why is the red one wrong? Sarah, what do you got?
Because it would not break if it's too low. Because it wouldn't. If it's too low, it just can't break it. It has to be really high.
There you go. Fantastic. Fantastic. This should take you 4 seconds at a maximum. Okay. Vivian, you should get this right. I believe in you. I'm gonna look for your name, Vivian. Did you get it, Vivian? Say yes. Give me a thumbs up. Okay, good. Okay, so we got four answers for the anode heal effect. Why is that one wrong? Anybody can just put your hand up. Sarah's got it. What do you got, Sarah?
The anode heal effect affects the side of the cathode being bigger than the side of the anode. The line focus principle is about the focal spot size.
Got you. When you say bigger, you mean higher intensity, I'm pretty sure, right?
Yes, yes, yes.
Okay, cool. Cool. Who's in the lead here? Sarah's in the lead. We got Ashley Henry's right behind. All right, let's see what we got. How is the anode angle related to heal effect? How is the anode angle related to heal effect? Did I make a mistake? Let me see. No, I did not make a mistake. Is this unclear for everybody?
Yeah, can you please clarify this?
Yeah, absolutely I can. Give me 1 second. Give me 1 second.
I got this wrong. In hindsight, I should have just stuck to your language. In the question, it says, "How are they related?" And the answer is inversely related. So just kind of keep it simple.
I made the same mistake.
That's all right. That's why we're here. That's why we're here. Can I pull this up or not? What's happening? Downloads. It could be I made a mistake too, but I don't think so. I don't think so. Not this time.
You explained really clearly earlier the difference of inversely proportional versus relation,
Right.
that was very clear, but the direct versus indirect, it's just you have to take longer to think, and it was like a 10-second click the right answer.
Got you. Got you.
I think that takes the most, you have to actually think about what happens.
Got you. All right. So if you think about, okay, let me use this one, and then I'll do my best at drawing. First, let me explain the difference between. Okay, I got it. I got it. Um, Imagine this is a seesaw. On one side we have, I'm gonna say Alan, and on the other side we have um, Nick Randa. It stands to reason if this guy goes up, this person's gonna go down. Those are directly proportional by the same amount. Sounds good? By the same amount he goes up, this one goes down. That's direct.
And down inverse. If
I'm
one goes,
sorry, inversely proportional. Well, whatever. These are proportionally related. Proportional related is a thing. I'm trying to differentiate
Same
between
amount.
proportional and related. So they're proportionally related. When one moves, the other one moves by the same amount. When you say one thing is directly related, that doesn't mean it impacts the other, but we don't know if it's by the same amount. So, for example, um, you tend to drink more water when you walk more. But we don't know if it's a direct proportional relationship. As in, is it 5 miles to 5 gallons of water? So the unit used to measure these, there's no quantifiable relationship, is what it is. We just know that one variable impacts the other. That describes a direct relationship um, um, definition. That's how you define direct relationship. One variable impacts the other. Direct proportional relationship means it affects it by the same factor. So if it's a factor of 2 in one way, it's a factor of 2 the other way. Is that good so far? Oh no, Sarah
The
did
difference
nod her head.
between inverse and direct, because you just said like impact.
Wait, say again?
Like, what's the difference if it even if it affects it one up, one down, that would be inverse.
Yes, yes. If we're going strictly by this, it's inverse. But I think the explanation was you want to know what's the difference between proportional relationship and just one that has some relationship between the two.
You explained that earlier. I'm asking the difference between inverse and direct.
Inverse and direct just means they go in the opposite direction. So one thing goes up, the other one goes down. That's inverse relationship. But direct relationship, one thing goes up, the other one goes up in the same way.
Can you explain that with the question that was just on the page?
Sure. So if this angle increases, then we're going to have less photons absorbed in the anode. So imagine, let me see if I can insert a shape. Let me see if I can insert a shape. 1 second.
You just said if the angle increases, right? So that means that the angle is more steep.
No, right here. Increases.
Increases.
Gets bigger. So imagine if, let's put this right in the middle. Let me put another one. I think this would be good. I think so. Now let's insert another shape. Okay, beautiful. All right, so this is starting out right about at the same spot, I think. Notice that let me make this more exaggerated. That's good. Let's make this more exaggerated too. All right, good. All right, so notice this angle is larger and the effect on the anode heel effect is less because less of the beam is absorbed on the anode side. So this is an inverse relationship. Where the angle is less, now we have more of the beam absorbed on the anode side. So that means the angle gets less, the anode heel effect gets larger. Is that clear?
Yeah, thank you so much.
Of course. This is why we're here. Chris, you good? Oh no.
Can I ask you a question?
Yes.
You good? Oh, he's good. Okay, Alan, what you got?
You said since the angle decreases, the anode heel effect increases, correct?
That's correct.
All right, thank you.
Oh, okay. Just want clarification. Good.
What does anode heel effect like if you say that anode heel effect increases, is that like I know what anode heel effect means, but what does it mean by anode heel effect increases?
I'm going to say 2 ways. That means more of the photons on the anode side are absorbed. That means there's a greater difference between the intensity on the cathode side and the anode side.
So that means more fat cat.
Not my term. Let me think about how to use that. Wait. I guess so. I just want to make sure you understand. That means that the difference between the intensity on one side or the other is more exaggerated on this side than on this side.
That's with a smaller angle.
That's with a smaller angle. You can see it. You can see it here.
I know you're using the triangles, but wouldn't on the anode on the smaller angle, wouldn't the triangle be more tighter? Because it's more damn, I don't know how to say the word. But wouldn't meaning the how the beam diverges, wouldn't it be more tighter compared to a larger a larger angle?
You would still get photons, but they would just be
It will
at a
be more
lower
stronger
intensity.
though,
So
right?
if I'm sorry,
it will be more not stronger. It will be more intensity, like you just said.
so if I were to draw this, say this would be photons of X-rays.
Mm-hmm.
On this side, you would have less. That's all
Yeah.
that's. So you'd still have the same beam width, but there would just be a lower intensity because some
Okay.
of these would be absorbed in here. See how this is touching? Over here, it's not touching.
Okay, I got you.
Got me? So I didn't have time to draw a proper triangle, but this I'll see you, Nick. 1 second. So this would be more exaggerated. Let me clear this. This would just be more exaggerated with a smaller angle, is what it's saying. Go ahead, Nick. What you got?
Can we go back to that picture of the angles?
This one, yeah.
Because to me, it looks like the anode one has a sharper angle. That's what I'm not understanding.
Oh, this is the angle they're speaking of. You know what? When I learned this many years ago too, that confused the juice out of me because I thought they meant another angle. They're speaking of this angle here, this one versus this one. You know what?
Oh,
I can do this better. Give me a second. Let me
okay,
do
I see.
let me do 1 second. Maybe I do a line, and then we can do. Let's do this. They're speaking of this angle here. Oh no. Speaking of this angle here. All right. This angle. Sounds good, Nick? You got it?
Yeah, I got it. Thank
All
you.
right, cool. You're welcome. If somebody have a question. Class is over, by the way. You're free to go. This PowerPoint, this Kahoot is available. You can go through as many times as you need to. If you have a problem and you have questions about it, just feel free to email me. I will respond as quickly as I can.
Thank you, Professor.
You're welcome. Anybody has any other questions, I'll stick around for 10 minutes for those who do. Go ahead, Chris.
Thank
The
you.
smaller the angle, the higher the anode heel effect.
The higher the, yes.
All right, thank you. Thank
Yeah.
you, Professor. Have a great one.
You as well. Thank you.
Thank you, Professor. Have a good one.
You as well. Thank you. I am here for about 10 more minutes for those who have questions.
Thank you, Professor.
You're welcome. Take care.
I got a question.
Go.
The things that you say that make the life longer for the X-ray tube is a cold room, you said, and an oil bath, and the oil bath in the X-ray tube.
Wait, that we can do to extend the X-ray tube life?
Yeah.
Warm up the machine and
Yeah.
don't expose it to high exposures when it's cold.
Okay, don't expose.
Another thing you could do, I forgot which group it was. It must have been you guys that you were told by a tech to prep the tube. Do you remember this
Yeah,
conversation? So
yeah.
you hold that first stage down so the
Uh-huh.
anode gets to spin up to speed, kind of thing.
Uh-huh.
That's one thing that you're supposed to do.
Okay.
All right.
I got one more question. I just don't know that. So the three stages of to make an X-ray, you said is the source of electrons, which is the cathode, and the voltage, and then the anode, which is which decelerates, correct?
Yeah, that stops the electrons. Yes, that's correct.
And then the fourth one, as Tasha said, was the vacuum tube.
Yeah.
Okay.
Some textbooks say that.
Okay. All right. Thank you, Professor. Enjoy
You're
your
welcome.
day.
Thank you. You as well. Kenny, do you have something for me? What do you got?
This is more in general, not just this class. I don't think you would know, but I'm just gonna ask ahead of time.
Mm-hmm.
Um, do you have an idea of how the finals are gonna be scheduled, especially with the radiation procedures and imaging class?
As in which days they're gonna be on?
Yeah.
I don't determine that. The school does.
Okay. Okay.
It does. But I know when they are. I could show it to you if you like.
Okay.
Let's see. Can you still see my screen?
Yeah.
All right. And I think you have this too. Maybe I'm mistaken. Let's see. 1 second. My thing, and then my folders, important documents. Class schedule. Is this the one? No, that's not it. Calendar. All right. Finals are gonna be this week. That's gonna be, looks like April, May, this week here, starting May 13th through the 21st, that week.
I have that calendar.
So you have it or you don't?
I don't.
Oh, you don't.
I have a different one, but I don't have that one.
Well, you probably have. You probably have. Probably have another one that looks like. 1 second. This one.
Yeah, I have that one.
Yeah, it's the same thing.
Because I mean that one just shows like it says finals are May 19th to the 23rd.
Yeah.
It doesn't show that it's also for I think that's Monday and Friday for next week.
All right, so May 19th to 23rd, right? So let's see if we can find the exact same one over here. Let's see if it says the same thing. I'm pretty sure it says the same thing because Dr. Gattis does not make these mistakes. Let me see. May 19th to the 23rd. So this is probably going to be your finals this week here, I'm thinking. And it's going to be the seniors, maybe. Probably what it is. So here's the juniors, that'll be the seniors. This is my guess. All right, but they will let you know. You will see a thing come out. But you're some ways away from the finals, though. You got 2 more quizzes, 2 more homeworks. All right, I think you'll be all right.
All right, thank you.
You're welcome. Hui Ming, Alex, Chris, Christian, you guys good? You got question or you comments? Wait for 4 seconds. 4. Alan, you got a question? You're back. What's happening?
Yeah, I don't see the cahoots on the web on the modules.
The Kahoot?
Yeah, for the practice.
I guarantee you it's there. So we just did physics, right?
Yeah.
Can you see my screen?
Yes.
Modules. Right at the top it says study guides will be placed here.
I don't see it in mine.
Let me view as student to see if there's something Oh, interesting. Thank you for pointing it out. You
Yeah,
can't
because I
see
was
it.
about to start studying that right now, and then I'm like, I don't see it.
I see. Thank you for pointing it out. So maybe it's just not published. That's what it is. Sorry about that.
All
Thank you.
right, thank you.
You're welcome. It
Appreciate it.
should be
Enjoy your
there now.
weekend.
You as well. Thank you. Sorry about that. All right. Christian, you good? I don't think Christian's here. That's okay. All right. You got something else for me, Kennedy, or you good?
No, I'm good. All right. Bye, Professor.
All right, take you, sir.